Right, let's begin. Hi guys, still meeting now a little bit. We've got Andy Magic Knight, Amok, Colt, C64 Psy, Stepz. Welcome guys. So I wasn't sure what to do tonight, so I thought I'd go with another Let's Code, because it's something I think can be a bit confusing for 6502 coders when they start, what the flags are and what they do. Thank you for the follow, Schlock, as well, by the way. Welcome to the stream, dude. So yeah, I just wanted to go through the flags, what they do, like when they are set, and the different branch instructions and how to think about compares. Hey Prince Phase, welcome to the stream. Anything new in the mail? No, I was kind of hoping I'd get the package from Protovision today, but I didn't. So I don't know if Mitsuyama's watching, but the Sam's Journey will come eventually, and I've figured out a way I can deliver without leaving the house. I can do a collection, so I don't even have to leave the house to deliver stuff, which is good. And next week, all going well, I'm going to try and get the bits together. I'm going to do a building the C64 Pi machine next week. So no wine on a Thursday, unfortunately. I do have some wine, but I'm not going to drink it. I know it's it's unusual. All right, let's talk about. Let's open the debugger, because that's the easiest way to see the flags. So, as has been printed into the Discord through the use of emotes, reactions, today, this is the flags, the NVBDIZC. Make it bigger, yeah, no worries. Yeah, it's quite small, isn't it? Oh, I wish it'd remember the size. It never does, unfortunately. So these are the flags. It's called the processor status. We have two instructions which directly save and restore that. It's ELP and PHP. We have covered them in the previous Let's Code series. Basically, the processor status is just another register, but it's a register with a special purpose. You can set things directly in it, some things anyway, and you can clear some things in it directly. But what it does is it allows you to work out the state of certain calculations or certain modes as well. So I'll just go through what each one of them is, what its name is, and I'll give you a very brief description of it, and then I will actually go through how each one of these gets turned on by the processor as it goes along. It's mostly automatic. The processor kind of sets these flags for you, but you do have some things that allow you to clear these, clear and set some of these flags as well. So each one of these letters stands for something, obviously. The first one is negative flag. I don't know why clicking on it does that. It does. That's weird. So this is set when the last kind of register action. So when you load something to a register, when you transfer something to a register, when you do an addition or a subtraction or an increment or a decrement, these flags are usually set. There is actually, let me share this. This is what I use for checking everything. Find it here, and I'll share this link. So this has all the opcodes on it, and this lets you know exactly what each of the opcodes, which flags they affect. So you can see here, all of the logic and arithmetic commands affect the negative flag. You see the little star in the negative column here. So anytime you do one of these, then the negative flag can be set. And the negative flag is basically bit 7 set of the last thing that you did. So if you did something on the accumulator, was bit 7 done. If you use an or AND or add or subtract, was bit 7 set. And the reason it's bit 7 is because if you've got a number in 8-bit and it's negative, then bit 7 will be set. And I'll go through that in a minute. I'll go through how to think about these numbers and how to easily understand, because you'll need it for overflow as well, which is the next one. So V is overflow. V is the overflow flag is only set by 4 commands. It's set by the addition, the subtraction. It's also set by the bit command and the PLP command. So whenever you pull the processor state, obviously it can affect all the flags. And the bit command can also set it. The bit command is a little bit unique in the way it deals with it. But overflow is essentially if a number overflows beyond the highest number it can display as a signed number and wraps back around. So if you've got 127 and you add 1 to it, you get 128. But 128 in 2's complement signed numbers is actually minus 127. So you've wrapped around and you've gone back to the beginning. That's called the overflow. It's useful for some things, but it's it's rarely used, to be honest. There's usually a better way of doing things in most cases, but I'll explain how that works, and I'll show you that in a bit more detail at some point. The next one is a blank, and that's because it's not used. Generally, it's always going to be 1. I think you can set it to what you want, because you can pull the value. You can pull this entire number. This is just a single 8-bit number. So you can pull it from the stack and you can push it to the stack. So you can actually change this number, but it doesn't do anything. The next one is the B flag, or I like to call it the break flag. This is a little bit unique in that it's the only one that you can't directly set through anything. The only reason it gets set is because you call a break instruction. It's a BRK instruction, and a BRK instruction will basically go and look for the break vector and launch that. Not important. We don't need to go through how that works. That's probably a topic for another day. So virtually we either consider we are working positive numbers, obviously ignore negative overtime. We don't care about them. Yeah, so hey Foro, welcome to the stream. So the processor doesn't actually care if you're working with negative or positive numbers. Everything it does is the same regardless of whether you're treating them as negative or positive numbers. And this is why we have the negative flag, and it's why we have the overflow flag. It's so that if you do want to use negative numbers, then you can get a bit more information about them. No, the break instruction is used. So if you do if you call a break, it will set this in here. You can find out what you have to do is you have to push the processor status to the stack, then you have to pull it back into the accumulator, you push it to the stack. So you do a PHP, and then you do a PLA, and then you can test that bit, and you can work out if you've entered a vector through a break instruction or through an IRQ. The next one is the decimal flag. So this is the one that tells the processor to do any mathematics in binary coded decimal. So instead of using binary, it uses binary coded decimal. Useful for doing scores and stuff. I think we have covered them at some point. I can't remember if you did them in the arithmetic episode or not, but maybe I'll do an episode on BCD at some point. That's quite useful. Interrupt flag. So this lets you know if you've fired an interrupt. This will also be set if the break flag is set as well. So if you enter an interrupt through a break, this will be set and this will be set. And this is how you have to check. Am I in a raster interrupt or am I in a break interrupt? You check both of these values, and then you can figure it out. Basically, this will get set whenever you enter a raster interrupt, and it will get cleared whenever you exit a raster interrupt. You can also set and clear it yourself as well, which is something I do at the beginning of every program, just to turn interrupts off so I can disable CIA interrupts and stuff. Then there's the zero flag. The zero flag is set whenever the result of a calculation or a load or a transfer, an increment, a decrement, takes the value in that particular register or that memory address to 0. I don't know why clicking on it does this. It's weird, but okay. And then there's the carry flag, and we've covered the carry flag quite a lot. The carry flag is essentially if the result of an addition basically overflows, but it takes the number, it needs to set a 9th bit, so the carry is like the 9th bit of an addition. So okay, right, so that's basically what they are. So let's go through, let's explain a compare instruction, and then I can show you why it's important to know what the different flags do. So let's just make a simple program. I'm not going to disable kernel or anything like that. There's really no need at the moment. So a compare instruction, there's 3 compare instructions. So let's save it as it's simple. So a compare instruction, as I say, there's 3. There's one for each of the main registers. So there's CMP for comparing the accumulator, CPX for comparing the Y register, and comparing the X register, and CPY for comparing the Y register. Now, you can kind of see all of these like a subtract command, and that's exactly what it does internally. It does a subtraction. So let's just do it with compare first, and I'll explain what's going on. So if I do compare, what actually happens internally is it takes the accumulator and it subtracts the compare value, and that gives us a value of 0, 1. Now, it doesn't store that value anywhere, but it does set any flags according to that as well. So looking at this, the flags it's going to set are negative, no. So negative will equal 0 because it's not a negative number. This would need to be 8 or above for it to be negative. 0 flag, no, it's not going to set. And the carry flag. These are the 3 that we're most interested in with these things. The carry flag again won't be will be set. Now, why is the carry flag set? And the reason the carry flag is set is because this is like a subtraction. So if you imagine the equivalent, this is the equivalent to doing set carry flag subtract 01. That's what it's essentially doing, except it's not doing anything with the accumulator. It's keeping the original value in the accumulator. And so the carry flag is set at the beginning because we're doing a subtraction. So the carry flag is set to 1, like so. And then when you do you subtract 1 from 2, the carry flag remains set. And so the carry flag is set here. And this is why when you want to do greater than or less than comparisons. Oh, here we go.
If Shallon True Return Parasol Stars Hazemaker Clyde GG Hazemaker Clyde GG Hazemaker.
Oh, I definitely need to put a limit on
Hazemaker
on the Hazy's text to speech.
GG Hazemaker Clyde GG Hazemaker Clyde GG Hazemaker Clyde GG.
Thank you for the bits, Hayes. And welcome to the stream. Is that it? No. Okay. Okay. There we go. Yeah. So this is why greater than and less than works. So if we look at this with different values, right? So just bear in mind that this comparison is essentially doing this here. Let me put. So if we were to make these, so this number is more than, so if the number is more than, then the carry flag is set. If the number is equal, then what happens? So we do a subtraction, the compare value becomes 0, which means that negative is still 0. The 0 flag is set to 1, and the carry flag is still set because we haven't gone below 0. So this comparison shows us that if the numbers are equal or greater than the compare value, then the carry flag will be set. If the number is less than, then what do we get? We get accumulator minus compare value. The accumulator is 0. We take 1 away from, we get FF. So now the negative flag is set because this is a negative number. The 0 flag is cleared, but the carry flag is also cleared. And the carry flag is cleared because we've borrowed, basically. It's the opposite of carry when you're doing subtraction. And so you can see that if the carry flag is clear, the number is less than, and if the carry flag is set, the number is more than. Very interesting. Interest comparison. Never thought the equivalent set. Yeah, it does. Yeah, it does essentially set the carry flag when you begin the comparison, and if the result of the subtraction borrows by dropping below 0, then it will clear the carry flag. And so what that means is you can do things like this. You can do branch of carry clear. So this is less than. And what I'm going to do is I'm going to actually do some stuff here. So I'm going to set more than or equal. This is just to show this working. Now, obviously, thinking about the carry flag like this, the reason I'm starting with the carry flag is because it's important to understand that this subtraction is happening. And if the subtraction is happening, it's a really good idea to understand how the carry flag is affected. So you can see here, right? If this value is less than this value, then we want to go to here, and we use the carry flag clear BCC to do less than, and we would do BCS to do more than. Obviously, we don't need to have this command in here, but and the way to think about this is if you think about these two commands alphabetically, you can think about it like this with the subtract, and you can kind of work out that 0, the carry flag would be set to 0. But the easiest way to remember this is if you think about this in alphabetical terms, then BCC is less than BCS. And that's the easiest way. So BCC is less than, which means BCS is the opposite of less than, which is more than or equal. Like so. So that's a really easy way to remember that. Think about them alphabetically, and you will easily just be able to say in your head, BCC is less than BCS. So BCC is less than. Very easy. And if we run that, we should hopefully get, because this is less than 1, so we should get a green border when we run this. There we go. And it's in NTSC mode. I need to turn that off. Don't know why it's in NTSC mode. There we go. BS. So that's the carry flag, and that's how you would you use the branches to check the carry flag. Now you can do other things here as well. So the carry flag is also useful if you do an addition. So say you've got a value here. Let's call it value 16-bit. Like so. Thanks for the host, Hayes. And we put a value into it here. Let's say this value is 2345. It doesn't really matter what it is. Let's put that in. Actually, let's make this quite high. So if I want to add a value to this, and I just want to add, say, an 8-bit value, then what I can do is I can load value 16-bit equals 0 because I want this section here. Thanks for the gift sub, Amok, and who was it to? C64 Sai, welcome to the subs. Thank you very much, appreciated, dude. So yeah, we're going to add an 8-bit value to this. So what you can do is you can do something like this. You can add a value like this. You can store it here. And then because it's a 16-bit value, what you need to do is you need to take the upper value and add 0. And the reason we add 0 here is because if this value, when it's added to here, goes more than FF, which it will do, because F0 plus 20 is 110, then this becomes the carry bit. So the carry flag is set at this point, which means when we do this addition here, we also need to clear it here. Always start with, whenever you do an addition, you need to know that the carry flag is at the right state. When we do this addition, it will actually add 1 to it. But what you can do, if you really want to save a few bytes here, is you can do a check here. You could do, if the carry is clear, then skip over this next bit. Otherwise, increment the value. And that will do this exactly the same thing by incrementing this value down here. Thanks for the host, Andy. Appreciated. So the carry flag is useful for a lot of things. There is another trick that you can do as well with the carry flag, which is, I should probably point out as well, I mean, I've mentioned this before as well, but you can set the carry flag and you can clear the carry flag with CLC, clears it, set the carry flag, sets it. You need to clear the carry flag when you do addition, and you need to set the carry flag when you do subtraction, which is why this is what happens with the compares here. So the other thing you can do, which is kind of nice, is if you've got a signed number, so say you've got this number, so this is minus 128. Andy with the gift sub, wow. Thank you, Andy, and welcome to the subs, Cakepocalypse as well. Cakepocalypse, that's awesome. Could do with some cake, actually. That would be good. Okay, so if you've got a number like this and you wanted to half it, normally what you would do when you half something is you would just shift it to the right. But if we shift this number to the right, the number that we're going to get out the other end is going to be 40, which for an unsigned number is correct, right? So half of this number is indeed 40. But if it's a signed number, that's not correct, because if it's a signed number, the actual number should be, let's just write unsigned there. Signed would be C0. And I'm going to explain the number line and how to think about 2's complement when we get to overflow. But just for now, just know, I can see chat for all the mobs from Andy's wallet. Oh dear. Yeah, so the if you were to half this number, this number is minus 128. So if you half that, it's minus 64. And minus 64 is this value. So this doesn't work for signed numbers. It works for doubling. If you have this number and you want to double it, so that's minus 40. You can do that and you'll get 80, and that's fine. So it works for doubling, but not for halving. So what you can do is you can very sneakily, you can use the carry flag here. So if you do a compare with 80, what it will do the subtraction. So let's do the subtraction down here. So it's going to do accumulator minus the compare value. So the accumulator is C0, the compare value is 80. So the compare value is 40 now. So that means that the negative flag is not set, the 0 flag is not set, but the carry flag does remain set because we never actually, C0 minus 80 never cross the boundaries at the end of the number, so the carry flag remains set. So what that means now is you can do a roll. And rolling that number now will take C0 and it will sorry, let's do it this way around. Actually, let's do it this way. So what we're looking for is E0 at the other end. So if we just did LSR, we'd get 60, and that's incorrect. But by doing roll, what we get is we roll it, which gives us a shift, which gives us 60, but then it adds whatever was in the carry as well. So the carry is set, and so it rolls that carry into the last position. So that becomes 80, which equals E0, which is half. So it's a really sneaky way to do to half these numbers. And keep the sign as well. So that's a really useful use for the carry flag, and one that you'll probably use quite a bit once you start messing around with those numbers. C0 is 192 in real numbers, but in terms of signed numbers, it's negative 64. So he knows me, the bastard. Yeah. So that's the carry flag. That's the reason I've done this one first, is because it helps to understand the way that this works down here. So let's have a look at the zero flag next. So the zero flag is one that you'll use quite a lot. So the zero flag again has two instructions to compare. It has branch if equal to 0 and branch if not equal to 0. Now, it's important to remember this is branch if equal to 0, branch if not equal to 0. It's not branch if equal, branch if not equal. It just happens that if you compare two numbers, then yes, they will equal 0, because if both numbers are the same, then the output here is going to always be 0. So this actually works perfectly. Branch if the numbers are equal, branch if the numbers are not equal. But it's worth remembering that what it's actually checking is if the result is 0 or not. So if the numbers are not 0, for instance, like this, then what's going to happen is we're going to get accumulator -2. That value is going to go to FE. The negative flag is going to get set. The 0 flag is going to be clear. The carry flag is also going to be clear. But you can see that the 0 flag is set to 0, which would imply that none of these numbers are not the same. Very, very simple. Probably the most used branch instruction you'll use. Well, actually, it's probably a toss-up between that and branch if carry clear and branch if carry set as well, because they do get used quite a lot as well. But certainly loops will use this quite a lot. You didn't realise that the branch is not equal. They are branch if equal to 0, yeah. And just to reiterate, you don't necessarily need a compare instruction. So if you look in this this list here, you can see that even just moving stuff around will affect these flags as well. So any load instruction will set the negative flag and set the 0 flag. Any transfer will also do the same. Pulling a value from the stack will do the same as well, as will additions. All of the arithmetic instructions will affect the negative and 0 flag. So it's quite possible to do things like this. You can load a value from memory, like so, and then it's immediately being compared to 0 in terms of branch if equal, because what you're saying is the last number that I put into the accumulator 0. So you can say branch if equal 0, branch if not equal not 0. And that's really handy to know, because in Z80 you cannot do that. In Z80 you have to actually explicitly test these things, which is very annoying. So I find myself only using branch if not equal, branch if equal, and no other one at all. I guess my code could be better. Yeah, I mean, branch if equal and branch if not equal are definitely the most common ones. I would say branch if carry clear and branch if carry set are probably the next after that. I'm just going to show you some examples of how to kind of efficiently use the branch if not equal. So if you're doing a loop, let's just say we want to do a loop 8 times. Doesn't really matter what we're doing. Let's store some characters on the screen, for instance, right? So this will put 8 characters on the screen. I'll demonstrate that quickly here. You can see we've got 8 A's up here. But if you look at what it's actually doing, it's every time it increments, it compares if that value has reached 8. And if it hasn't reached 8, in other words, if the value in X isn't equal to 8, then it will just jump back to here. this is inefficient, because what this means is every time this loop runs, every iteration of this loop, it has to do this compare instruction. Remember what I said about the 0 flag being set automatically. So what you can do is you can go the other way. You can go backwards. Yeah, I'll demonstrate it this way, but it's not going to be quite exactly the same because I need a different branch instruction. But I'll show you what I mean. I can print 8 characters to the screen. They'll be shifted over by 1 because of the way the loop works. But you can see I've taken the compare instruction out, and that's because whenever I do this, the 0 flag is set. Actually, I need to go backwards as well. So you need to go backwards through the loop. So this will count down from 8 down to 0. So when it reaches 0, the 0 flag will be set, and this branch will no longer happen. Which actually gives me a nice explanation for moving on to the next one, the next flag comparison instruction. I feel like this is going to go really quickly, you know. I'm going to run out of things to talk about. I've got a couple of extra things we can discuss, so it's fine. So this is a problem because I wanted the character to start here, not here. So what I could do is I could do -1 on here, and then it would display in the correct place. Like so. Or what you can do is you can use another flag. So we have the negative and positive flag, the negative flag basically, and that has 2 instructions that deal with it: branch if positive, branch if plus, branch if minus. So branch if plus is basically if the number is from 0 to 7f, then it's positive. If the number is from 80 to ff, then it's minus. And so what that means is we can very easily, if we would just reduce this down to 7, when we decrease this will go 7, 6, 5, 4, 3, 2, 1, 0, and then it will go to ff. And so the number becomes negative. So at that point, we can just do, if the number is positive, keep going, and this will just loop through until the number is no longer positive. But again, we don't need the compare instruction. If you run out of things to talk about, I'd like to know how to draw 1 screen from charpad by see if you have 3 drawn side by side. Yeah, I honestly would recommend getting the Thalamus edition of charpad. It's a small, I mean, it's what, like £20 or something like that. It's absolutely worth it, 100%. Because it allows you so there's a thing in the Thalamus edition of charpad called Flex Grid. And what it does, it allows you to draw a massive map all on one thing, like you've got, Hayes. No, they did, but the thing is most flick screen games will still arrange the data as screens, so it will take the stuff from charpad, and they'll have some extra processing which splits the data up into individual screens. That's why I have my own tools, because charpad isn't really good enough for doing that kind of flick screen thing easily, and FlexGrid solves that. And what FlexGrid lets you do is lets you draw a huge map, and then you can set the size of a screen, and then when you export, it will export individual screens for each one of those. Yeah, nice example. Yeah, it seems going backwards. Backwards is definitely more efficient. But it also depends as well. So say I want to draw 255 characters on the screen, I can go forwards. It really doesn't matter, because if I'm filling 255, all I need to check is the value 0. So I start at 0, I store it, and then I increase it. So the first time it does the check, the number is 1, and it will keep doing this check until the number becomes 0 again. So this will draw 255 characters on the screen. It's just about thinking about how your loop works, and trying to avoid compares is a really good way of increasing the efficiency of your loop. I'm going to show you another use for branch of plus and minus in a minute. Let me just get this running. There you go. So it's drawn 255 characters, and this works because it it goes through every value once, and the last value it gets to is 0 as it resets, and then it can reset properly. Okay, so I'm going to show you another good use of the branch of plus and branch of minus, and using the 0 flag. So what I'm going to do is I'm going to create a value 8-bit here. So say you've got, and this is something I've done a lot, and I should remember to do this, and I don't. And I looked it up again before I started the stream just so I could remember how to do it. And I should really go through a lot of my code in the Saturday game and implement this stuff. But let's do it here. So if I want to add this value to here, right? So let's go through it again. So I'm going to load. I'm going to clear the carry bit. And I'm going to load value 16-bit plus 0. And I'm going to add value 8-bit. Store that here. And I'm going to go the old way. I'm not going to do the efficient way that I explained before. I'm just going to do bog standard way of doing this now, which is I'm going to take the upper byte, add 0 to it. Okay, so this is great if I want to do unsigned edition. It's absolutely fine. Let's run this in the debugger so you can see the value. Oh god damn it, I have to make it bigger, don't I? Okay, let's go and find it in memory. It's kind of annoying if I to find this. So this is the number here, 2410. So it's taken 23F0 and it's added 20 to it. But what if I want to go backwards, right? If I want to go backwards, then this is going to break a little bit. So if I did E0, I basically want to take 20 off this. So this should go down to D0. So the value in that location should be D0. Let's go find it again in here. Oh, actually, it has worked. Oh, no, it hasn't worked. You see 24D0. It should be 22D0. So what it's actually done is it's incremented this value here. Now, what you can do is you can do some comparisons here. And you could change this into a subtraction. Or what you can do, if you load the 8-bit value here, and if it's plus, actually do it with the X register. There we go. If it's plus, we'll jump to here. Let me indent everything here. There we go. And instead, what you do is you load. Actually, we do it with the accumulator here. There we go. Hang on, let me think about this. Actually, no, you wouldn't do it with branch plus. You would do it like this. You would AND this with 80. So we check that the upper bit. So it is kind of we're kind of checking if it's positive or negative, but we're going to do it with AND. And if it's equal to 0, we just jump straight to here, which means if it's equal to 0, that means this number is positive. And we just do that. Otherwise, what we can do is we can load the accumulator with FF. So to explain what this is doing, this isn't using the plus, this is just using and equals. I can't believe Flipswing says it's so common you have to buy a tool made in 20. You don't have to buy a tool made in 2020. What you have to do is you either have to draw individual screens one at a time in Charpad, or you draw a massive screen, and then you write an extra little script which will take it out and strip it into individual screens, or you write slightly more complex code to deal with a larger map, and offsets into that map instead. The data format is just exactly what is in the game. You know, it's just a binary file. I think you need to probably understand how you're actually drawing that data on the screen in order to be able to understand how to edit that data, and split it up. But the map is just from left to right, like a book, tile numbers all the way across, and so on and so on. So if you want a particular screen, you need to know how far across, how long each line is. Yeah, you need to understand the data the screen code is reading from. It's all in the PDFs. It is in the PDFs. But if what you can do is just make a very, very small char pad with like 3x3 tiles, and then open it up in a hex editor, and you'll understand it almost straight away, I reckon. But every horizontal line will be consecutive in memory. That's the thing. Okay, so what this is doing a signed addition. And the way that's working is it does the bottom byte, it does the least significant byte, same as usual. But then what we do is we check if the value that we're trying to add is negative or not. If the value is negative, in other words, if this fails, then we set the value to FF for our addition. If the value is positive, then if the value is positive, then the accumulator at this point will be 0 because we've added it, and so we add 0. So basically, the upper byte either has 0 added to it or FF added to it, depending on whether it's positive or negative. And this should give us 22D0 when we run this. I'll leave this actually in the code because this is quite a useful one. Yeah, it does have a text export as well. Yeah, I honestly definitely recommend the Java, because you also get access to the new sprite pad as well, which is much better than the old one. So let's go and have a look at that memory location. Where is it? There it is, 23D0. So you can see how that's now actually done the subtraction properly. And that's much neater than other ways of doing it. So I've been doing this in crazy ways, like having 2 different branches on whether this value is positive or negative, and it gets a little bit messy. So it's not made crap on purpose. The original charpad was free for years, and it was enough for what most people did. But I think Thalamus came along and went, well, it'd be really handy if we had this and this and this. And the dev behind charpad spent a long time and a lot of invested a lot of time in making a better version, and then was told you may as well sell this because it is pretty decent. I think it's fine that I think it's fine that it does that. Does it make a difference that the 8-bit number has been No, it doesn't. And the reason it doesn't is because if you imagine this number as a word, it's actually that as a word. And because it's least significant bit, that would be like that in bytes. So it doesn't change the way this works. But yeah, I should have probably registered it as a byte. But I mean, if you're only using an 8-bit value, use a byte. Don't use a word. It's a waste of space, basically. Cool. Okay, so that is basically the negative, the 0, and the carry flag. So let's talk about the overflow flag. So the overflow flag is a bit of a different one. So if we look at the number line, let's put an actually I'll leave this in here. You can actually extend this to 16-bit as well if you want to, but to extend this to 16-bit, you have to change this little bit here. If I get some time, I'll show you how to do that as well. But for now, it doesn't really matter too much. Okay, let's just comment this. Actually, let's leave it there. It really doesn't matter because I can just put another RTS here. There we go. Okay, so let's think about a number line. So I'm just going to draw what I hope kind of roughly looks like a number line. And so if we think of our 8-bit numbers, they run from 0 all the way up to 255. Or in hexadecimal, 0 to FF. And I'm even going to put the binary in. You'll see why I'm putting the binary in a minute. It's quite important. Oh my god, there we go. So this is a basic number line. Everybody's done number lines in maths at school. This is exactly how it works. So if an addition of an 8-bit number goes beyond this point here, the carry flag is set. If a subtraction goes below this number here, then the carry flag is cleared. But if this is a signed number, however, then this is slightly different. So I'm not going to put all of the numbers in here. I'm just going to put the decimal numbers in here. So if this is signed and this is 0, and this bit in the middle here is actually, let's put 2 lines in here. You know, 58 years. You went to school, Andy. I'm impressed. That's kind of quite fancy for a northerner. Okay, so with a signed number, we basically go up to 127, and then we start at minus 128. So there's a break in the middle here, and that break comes when these binary numbers go from oops, it's kind of awkward doing this in the text editor. So what happens is the binary numbers count all the way up until all 7 bits are full, and that's 127. But then when this next bit gets set to 1, then we start at minus 128. So why do we start at minus 128? Well, the easiest way to think about this is if we go all the way to the end and we fit the other side in. So 255 becomes minus 1. And then if you imagine taking this line, in fact, let me just copy this. And let's get rid of the numbers up here. So we've just got our binary numbers in and our numbers. Now, if you imagine taking the number line and just splitting it in half, so like this. So now we've got 2 halves of a number line, and basically swap the 2 lines over so they become continuous. So basically this, let's try and get this right. Tabs have made this a bit awkward. I should have done this with spaces. There we go. So all we've done is just swap those 2 halves of the number line, and you can see now the numbers are continuous all the way from minus 128 all the way up to minus 1 and 0, and then all the way up to 127. And so that's how we think about minus numbers. It's called 2's complement. There's other ways to think about this, and there's definitely other people who will give you different ways to think about the 2's complement system. But I think this is the easiest way to think about it. And the reason I like this system is because it also helps you think about the carry flag and the overflow flag as well. So if I put a C here, why is that C there? That C basically means that if we cross this boundary here, if we cross between these two, regardless if it's a signed number or an unsigned number, remember the 6502 doesn't care if you think the number is signed or unsigned. All it cares about is its binary representation. So if you cross this point on the number line, in other words, you go from all the bits set to all of them clear, or all of them clear to all of them set, then the carry flag is set accordingly. So if you go from 0 to 111, then the carry flag is cleared, and if you go from 111 to 000, then the carry flag is set. Likewise, the overflow flag sits on these ends as well. Now, the overflow flag is basically either clear or set, just like the carry flag, but it doesn't care which way you go from here. All it cares about is that you have crossed the ends of this timeline. So in terms of this, the overflow would be here, and the carry flags would be here. But it's easier to think about it like this. So if your number overflows off the end of the number, you've gone from 127 plus 1 gives you minus 128. That's obviously incorrect, and that's an overflow error. And it's rather than throw an error, because it's not really, as I say, the processor doesn't care if you're using negative or if you're using signed or unsigned numbers. This will just tell you that the result of this calculation has overflowed for a signed number. How do you change a signed number to an unsigned number and vice versa? You don't. It's how you interpret it. So if you've got a number like 128, for instance, but you want to represent that as a signed number. Now that's off the top of here, right? So what you would have to do in this case is, if you add 1 to this and you want it to be 128, it's going to give you minus 128. So what you then need to do is you need to say, okay, I'm going to check the overflow flag. So you will do branch if overflow set, and then you would adjust 16-bit sign. But I'm not going to get into how to do that. I don't think it's that important. Mostly negative, positive numbers, you probably won't use the overflow flag at all. This might explain all my bugs. So one of the common things I see is people doing things like this. They will do, they will take a number, say 01, and they will compare it against a number like 90, for instance, right? Let's do C0. So we're checking the number 1 decimal against 192. Now, say I want to check if that number is less than this number. The correct way to do it is to say less than. So BCC is less than BCS. So BCC, so branch if carry is clear, less than. And this will work. In fact, I'm just gonna comment this out, and I'm gonna run a little test here. So let's put less than here. So if it's less than, it'll go green. If it's not, it will go red. So if I run this code, we should see a green border. But what I see a lot of people do is they will use this instead. And that's wrong. And the reason this is wrong, we'll go through the logic for this in a minute. But the reason this is wrong is because you're actually checking the negative flag. You're not actually checking the distance between these two. You're not checking which one is higher or lower. Sorry, you're checking the negative flag, and you'll see when I run this, we get a red border. So it's not the same. So let's go through what I said down here. So let's copy this and let's explain why that is the case. So we're doing a comparison. Comparison basically does this. So we take the accumulator, which is 1, and we subtract the compare value, which is C0. So that gives us BF. C1. The negative flag is set because, hang on, is that right? That shouldn't work. Hang on. Set the carry flag, yeah. Subtract C0. That should not. I'm trying to figure out why that fails, but for some reason I can't. That should fail. I'm confusing myself now. I can't explain why that doesn't work. So it does a subtraction, so it subtracts this from this, which gives you C1, which is minus. So this should jump to here. Oh my god, my mind is blown. I think I found a weird caveat for the subtract rule. Can anyone explain why that actually fails? Because for me, that seems... One minus C0 will be C1. Because accumulator is 1, compare value is C0. So if we go from 1 here and we minus C0, we go all the way to BF. But oh wait a minute, no, I'm just adding the wrong freaking numbers, aren't I? That's what I'm doing. Yeah, okay. No, it's me being stupid. It should be 4-1. There we go. It's just my maths. It's terrible. So just to demonstrate that in the calculator, just to prove that I'm not going insane. So we put hexadecimal in here and do 01 minus C0. Oh, it's done 2's complement all the way down. But you can see if you just take the last bit here, 4-1 is the value here. It was just me being stupid. All right. Whew, thank God. Yeah, I was beginning to panic then a little bit that something had gone wrong. Yeah, so in this comparison, what happens is we take C0 from 0-1. The result is 4-1, which means the negative flag is not set, the 0 flag is not set, and the carry flag is cleared as well at that point. But that means that this is not negative. This is not a negative number. So you can't use, when the distance between the value that you're testing again and the value that you're testing it against is more than this 127 on the timeline on the number line here, then this won't work. It will work for numbers less than that. So if I did this, for instance, this would work, and that's fine. But the moment this gap between these two becomes more than 7F, so it's fine there. And if I do 7F, it will be fine as well. In fact, if I do 80, it will be fine as well. The moment it becomes more than 80, it's going to fail. So the moment this becomes that, it's going to fail. And that's why you need to use the carry, because the carry flag is the only one that's going to give you the true indication of whether a number is more than or less than. Let's see. What failed with the branch minus now works with BCC. So that's why you use BCC. Weirdly, Hayes, it's kind of the opposite. It's usually the maths that is a problem when I'm drinking, but for some reason the maths, I just got the maths completely wrong then. Yeah. Very, very strange. Anyway, that's how to think about negative numbers with these number lines. They will definitely help you kind of understand the overflow flag and even the carry flag. You can, like I say, you can think of the carry flag as just like a little switch that sits in the middle of this timeline here, in the middle of this number line, and when the value crosses it, it flicks the switch either on or off. And the overflow flag is exactly the same, except with the overflow flag, anytime you cross that, it gets switched on, no matter which way you go. And you do have a clear overflow flag, so you can clear it before you do any of these calculations. There is no set overflow flag, so there you go. Right, I'm going to go for a quick smoke, and when I come back, I'll have a think what I'm going to discuss, because that went really quickly. I was thinking it was going to take a bit longer. I hope that's been kind of clear. If anybody's got any questions, please let me know in chat. It's kind of I worry sometimes that I explain things using my brain and not thinking about it as a beginner. So I need to make sure that I do think about it from the beginner's point of view. So if there are any questions, let me know. I'll be back in 2 minutes, guys. Be right back. Right, I'm back. I'm going to try and keep this at least semi-useful, this file. Just going to put some stuff in so it's obvious what it is.
1, 2, 3.
Okay.
Brilliant.
Oh, thank you for the
Thanks
bits,
a lot.
Amok. Very much appreciated. I can't tell if there's any questions because you guys have been gambling, so... Okay, cool. Seems there's no questions on that. All right. Okay, let's talk about cycles as well. So one thing that's worth knowing is if you're doing something which is timing critical, so say you're doing something like the raster bars demo that I use as the BRB, then you need to make sure you use the right number of cycles per line. And so it's worth knowing how branch instructions work with that. So if I get a value 0, and I do this, right? So loading a value takes 2 cycles. Now branches are a little bit different. So a branch will take 2 cycles if it's not taken, and 3 cycles if it is taken. So in this case, the value is 0, which means this branch is not taken, so 2 cycles. So this whole thing here takes 4 cycles. However, if this becomes 1, then this branch is now taken, and now it will take 3 cycles. So it's worth knowing that. It means when you do a loop like this, for instance, which is a common kind of time wasting loop, you'll do something like this. I don't know why I keep putting RTS on the end, it doesn't really matter. So let's count the cycles in this. So this takes 2 cycles, and then on the first iteration of this, the decrease always takes 2 cycles as well. And then this will take, because this is non-zero, this will take 3 cycles, and it will jump back to here. And then it will repeat this again. Now X is 2. And so take 2, 3, and so on. But on the very last one, the value has now reached 0. 2 to 2 to 1 to 0. So instead of 3 cycles here, this will take 2. So it's worth knowing that when you're looking at loops like this, that the very last iteration of the loop will take 1 less cycle because the branch is no longer taken. Very important to know. There's another caveat with this as well, which is if your branch crosses a page boundary. What do I mean by a page boundary? So the pages are basically memory address, the upper byte here of the memory address. So this is page 1. It runs from 0, or this is page 0. Sorry, we call it 0 page. In fact, it runs from there to there. This is page 1. It runs from there to there, and so on. And so what do I mean by crossing page boundaries? Well, if this branch is at address, let's just say this is at address 100, that means that this label here is actually at 0FF. And so that means that branch is crossing a page boundary. So what will happen here is an extra cycle gets added for any branch that crosses a page boundary. So in this case, this will be cycle 4, and this will be cycle 4. This will stay as 2 because the branch doesn't get taken and it just drops down into this row. So it's worth knowing when you do critical timing things exactly where you are in memory. And that's why we have this command here. We have the align command. And that basically makes sure that everything starts at, well, basically XX00 basically. So if I did 80, then it would start either XX00, XX80, and so on. It's just making sure that the next piece of code is aligned with exactly the right place, and this is important when you want to do tiling things. So it's good to know that about branches. Again, that is explained, I believe, in the in this thing here. I think if you look down, yeah, here we go. So you'll see in this list here, if I just search for branch if not equal and find the first iteration of it here, you can see here it says two cycles. So branch is 2 cycles, but it has got a little star next to it, and that star means add 1 cycle if a page boundary is crossed, add 1 cycle if a branch is taken. So it does explain everything in that as well, so it's handy to know. Have you covered logic operators and or EOR? And if you may want to refresh you a ton of time at the end, to bit 9 of price X. Oh, you mean sprite X? Okay. I think we did that I think I did that in the logical operators, but maybe I will do. I should probably do an episode on sprites specifically, because I think sprite manipulation can get a bit confusing when you start dealing with that 9th bit. But I can maybe do an episode on sprites, I think. When is my next 12-hour game coding live stream? So yeah, I kind of want to do this fairly soon. I mean, this is, I kind of need an excuse to do it, and my excuse this time is that my YouTube subs has gone over 1,000, so that's probably why I'm going to do it. But I'm going to run out of reasons to do it soon, so I'm just going to end up doing them randomly, I think. But I'll probably do one next month, I think, at some point. Somebody had I don't know who it was, but somebody had the idea of combining the giveaway with the marathon stream. So maybe I'll do it on the marathon stream as well. I need to work that out, because if I do a marathon stream, then the giveaway is going to be open for much longer. So I might have to increase the ticket price a little bit, just to make sure that loyal viewers have got a higher chance than those who just come along for the giveaway. I'll have to calculate it. I'll have to work it out at some point. I don't know. Okay, I think what I'm going to demonstrate now. I'll show you some. I'll show you some tricks that you can do when you're doing using branching. So one of the most common things you might want to do is you might want to read a value. So let's say we read this value from here, and if the value is not equal to 0, then we do something. Yeah, and this, it doesn't really matter what's in here, so I could just put some knobs, really doesn't matter. But you might have a need to do something else. Okay, now what I see, what I do myself as well, everybody kind of does this, is I'll do something like this. Okay. Now the problem with that is this takes 3 bytes up. Now if you want to save a byte, then the easiest way to do this is, you know that the 0 flag is going to be set here, so you could just change this to branch if equal. And now, because these are relative, actually I should probably explain the branch instructions. Anyway, good night, Bitmapsoft. Thanks for joining the stream, dude. Yeah, it's kind of, I was a bit worried this would be a shortish kind of explanation. It has kind of turned into that. Hey, old school coder, welcome to the stream, dude. Yeah, so try, instead of using jumps in places, try and use branches where you can. If you know the state of something, try and use a branch. It's not the best example here, because what you would probably do, you probably have this code actually up here instead. But the point is if you want to jump around and it's close by, then try and use branches where you can. You'll save some. You get lines for being late. Yeah, you'll save some bytes by doing that. Let's explain a little bit about how the branch works. So let's just put some random crap in here, and let's go and have a look at what actually happens here. So normally when you do a jump, you will jump to a location like this. And I know this is jumping to the same location, but I just want to show the difference between these two instructions when we look at it in the disassembler. So let's go and have a look at that code in memory. Oops. So here's our code. So let me put it in this view. It's a bit easier to see in this view. There we go. So here's our branch instruction, and here's our jump instruction. And here's the cycles here as well. You can see it's how many cycles it's taken. It actually doesn't put the branch cycles correctly. It's a little bit funny like that. It only puts the branch not taken values in here. But you can see from this, so with the jump instruction, we do have 4C, which is the opcode for jump, and we have the address 0819 stored in little endian format here. But the branch instruction doesn't have that. The branch instruction has this 03. And the reason it has a 03 is because what it's actually doing is it's working out the distance from this instruction to this one. But if we take the position here, right, we're at 0814 and the branch is pointing to 0819, the distance is actually 5. So why is it showing 3 here? Well, the reason it shows 3 is because it actually takes the distance and it takes 2 off it. And the reason it takes 2 off it is because this instruction, where is it, is 2 bytes long. So it's actually taking the next line, not the line that you're on. So it's taking this line here and this line and subtracting the difference. And it gives us 03, and that's why we get 03 in here. This is why branches will only go 127 bytes forward and 128 bytes backwards. It's because it's using a single byte. It's called relative addressing, and it uses a single byte to represent a jump through the memory. So I guess that will lead us on to the next little trick, actually. So that becomes a problem if you want to jump further. Let's put an RTS in there. Say you've got this set up here, and then in the middle here you decide to put 128 bytes of data. This will no longer work because now the distance between here and here is greater than 128, and you'll see when I compile, it complains that the relative address is illegal. Jump distance is too far. And that's because from this point here to here is 129 bytes, and that's too long to represent as a single digit on our line. You can see here we can go from minus 128 to 127. So this is going to fail. And so a trick, I've said this many times, but I will explain it again. The trick to this is you can you basically invert the condition here. So what you do is you invert this condition so it becomes a branch if equal, and you jump to a temporary label like that. And then on the next line, you jump to the original label that you wanted to jump to, and then you put your temporary label here. So this does the same thing. You're basically just inverting the condition. Now, what I've seen some people do is they will have a sudo command. So let's explain sudo commands a little bit. So in Kick Assembly, you can make your own commands, and the way you do this is you give it a name. So I'll call it branch if equal long, branch if not equal long. There you go. and there's the address that we want to jump to. Oops, branch not equal long, and then like so. And so all we need to do in here is we need to write the code. So this is like a macro, basically. We need to write the code that does this. So what we'll do is we'll say, okay, branch. So we invert the condition, so it becomes a branch if equal, and that becomes to a temporary label just ahead here, and then we jump to the original label like that. So you can make a sudo command to do this, and now you've got you don't have to invert it if you don't want, but I prefer to just manually do it. It's fine, but this should work. Valid token. Oh yeah, sudo commands don't actually have brackets around them. There we go. There you go. That works. That does the same thing. And that applies to all the branch instructions as well. So if you've got a branch plus and it's too long, switch it to a branch minus, jump to a label just ahead, and then on the next line do a jump to the original label. If you've got a branch if overflow clear, switch it to a branch if overflow set. If you've got a branch if equal, switch it to a branch if not equal. If you've got a branch carry clear, change it to carry set, and so on and so on. Very, very easy. Now, thankfully, on the Mega 65, actually, there are two forms of relative addressing. There's 8-bit relative addressing and 16-bit relative addressing, so you don't actually need this. On Mega 65, this will work, and what it will do is it will just add a 16-bit relative address instead. So it's kind of nice, and I've got that set up already in the sudo commands library that I've made for the Mega 65, so that's kind of cool. All right, what else can we do with compare branching as well? Oh, I know. So I saw something today. I was looking through some bits of code for some nice tricks, and I saw something which I kind of want to use now. So one of the things we might have is, I don't know, like player invulnerable, right? And we might have a byte here. And we might use this as a flag for determining whether the player is invulnerable or not. So what we'd normally do is we would do something like this. We would, to set whether the player is invulnerable or not, we would do this. And to clear the player invulnerable flag, we would do this. And to test the player invulnerable flag, we would do branch if not equal. Like so, right? So that's quite a common way of kind of doing flags. But what I learned today, let's put these in here, was a different way of doing this. So if you're gonna waste a whole byte to store one value like that, then it doesn't really matter which bit you set, right? As long as the value is 0 or non-zero, then this will this will work. So what I've seen as a kind of a speed way of doing this is instead of setting 1 to the value, let's just write a better way. Instead of writing 1 to the value, you write 80 to the value instead, like so. So why is that good? Well, first of all, it means if you want to clear it, you can just do logical shift right like this. And that will clear it. Now you could, in theory, you could just do arithmetic shift left of this one, and would do the same thing. It would also clear it. But here's where the cool thing comes in. So what you can do if you want to test it is you can use the bit instruction. So the cool thing with the bit instructions is it does an AND against well, it doesn't do it tests whether or not the negative flag is set on something. And it's kind of like an AND, but you can do it directly like this. So what you can do is you can do bit player invulnerable, and then you can do branch if minus player is invulnerable. So here we're using the branch if minus by checking the negative flag to check if something is invulnerable. But the advantage with this is, with the old way of doing it, you're actually using the accumulator. You have to use the accumulator. There's no other way of doing it, and you end up basically bashing the accumulator, and you can't keep it free. This way, you can still have something in the accumulator, and it will remain there. I can put this in here, and it will still be 2 there. Whereas if I did that here, obviously it wouldn't work. So this is a nice, neat way of doing flags. It's something I kind of want to make a bit more use of at some point, because I think it's quite a neat way of doing flags. And I do have quite a lot of them in the game, and there's probably quite a few bits of code where I'm having to push accumulator onto the stack, like do stuff like this. To push and restore it, and then I have to like pull it again when I'm in this function. It just gets messy. Whereas this kind of avoids having to do that at all. So I'll keep this in here because this is a nice little piece of code, and this just relies on that 0 flag. I think while we're at it, actually, I'll explain the bit command in a little bit more detail as well. So what bit does is it will take a value, and it will test the bits of that value against it. Right. So what it does is if you give it a memory address like 2000 or whatever, it will take the value that's in that memory location. If bit 7 is set, then it sets the negative flag. That's something we're used to. That's absolutely fine, and we're used to doing that. However, if bit 6 is set, it sets the overflow flag. And this is a very odd use of the overflow flag, but you can use it for testing bit 6 as well. And it does work like AND as well. Again, you can kind of look this up on here. It does tell you in here exactly how it works. Where is it? Bit here. Yeah, and the 0 flag as well. So the negative flag is if bit 7 set. The overflow flag is set if bit 6 is set, and then the 0 flag if accumulator and the memory. So I'm going to write there. So it actually sets those 3 flags, and you can use it for doing all sorts of stuff. It is a really strange instruction, but it also has some other good uses. In fact, I'm going to show you another good use of it now as well. So the cool thing about bit is it actually doesn't change anything in the accumulator, right? So on line 21 should be LSR. No, so I'm showing how to clear a flag if it's set to 1. So if you use 1 as your set value, then you can use ASL to clear it. Actually, no, you're right. It is LSR there. That should be ASL. That's why. So it's the wrong way around. Yeah, thank you. Yeah. Actually, it doesn't really matter which one you use here. You can use ASL or LSR. Both of them will make this non-negative, so this will still work. But you're probably better off using ASL so it becomes 0 in case you want to give it a 0 test at some point. Okay, so that's let's call it custom flags. That kind of explains how that works. So another great use for branching and the bit instruction is if you've got, for instance, say we want to set a value in X if the player is invulnerable, and we want it to be a different value if he's not. So say we want X to be FF if the player is invulnerable, and if it's not invulnerable, we want it to be 0. So what we could normally do is we could do something like this. We'd say, okay, so if the player is invulnerable, then we'll jump to here. We don't do anything. Can act on it there. I'm confusing myself now. I'm confusing myself. Ignore that one. Okay, good night, Cake Apocalypse. Oh, what was it? There's a real sneaky way of doing stuff here. And I cannot for the life of me remember what the hell it is. Oh, it's if I want to use the same register, that's why. Right, there we go. So you might see something like this. So basically, I'm trying to just use one register here. But the problem is if I want to change the value based on player invulnerable, I can either use some lookup table or something to grab the value directly. But say the values don't make any kind of direct mathematical sense. I just want to set FF if it is equal. Sorry, if it's not equal. If player is well, either way, right? I want to set FF or 0, 0. This is kind of a little bit inefficient, but what you can do is you can do. Let me remember how to do this now. Yeah, okay. If you get rid of this, and instead you put the byte 2C here. What this will do, so if the player is invulnerable, in other words, if the value is non-zero, it will jump to here and it will set the value to 0 and everything's fine. However, if the value, if this branch is not taken, it will come to this point. So this will set the value to FF, and then this next line, this is the bit opcode. So what the compiler actually, what the 652 actually sees when it gets to this location is not this, but it actually sees this instead. It sees bit 00A9 or something like that, and this does nothing. So basically, this basically gets to this instruction. It just wastes 3 cycles and doesn't set the accumulator at all. So this is an easy way of doing this kind of toggle between 2 values without using a jump instructions as well. So this will blow your mind. What will blow your mind? I'm intrigued now. Oh, do you mean this, the 2C thing? Yeah, I could just XOR one, but say I wanted these values to be. Then how does that work? You know, you can't. If you want to toggle between 2 values that don't have any mathematical correlation to this value here, then this is an easy way of doing it without kind of having that jump in the middle as well. It also takes less bytes as well. So I'll explain it again. So what's happening here is basically we're checking to see if the player is invulnerable. If the player is invulnerable, so I'll just put some notes here. So this is the value we want to set the accumulator to if the player is not invulnerable. This is the value we want if the player is invulnerable. So what happens is if the player is invulnerable, it jumps straight to here and runs this piece of code and then carries on down here to the RTS or whatever. If the player is not invulnerable, this branch is not going to get taken, and instead it's going to come to this instruction. So this is going to set the accumulator to E3. But then what the next line does is it convinces it doesn't convince, it tells the the 6502, then it needs to run a bit opcode. So this is the equivalent of this without that in there. And so now it loads the accumulator with E3, and then it does this bit command, which does absolutely nothing. It just sets some flags, but it doesn't change the value in the accumulator. And that's because 2C is the bit instruction. So in fact, let's load this into the assembler and show you. Why is that failing? Probably got some weird. Oh, I've got a label here. Okay, it's just yeah, whatever. Yeah, the bit instruction is really useful, and you can use it to do lots of cool stuff beyond just kind of setting flags and stuff. So let's just go and have a look at that code and show you what's going on. Okay, so let's jump to 0801. Okay, so here's our code, and you can see how it's interpreted this line as bit 27A9. Sorry, not 27, because it's 27 here. Because of that 2C. So if I go into here, you see the 2C on this line here basically says, okay, the next instruction is bit, and it's got 2 bytes that come after it, which is the address. However, if I don't know if I can make it actually look at that in a different way. No, it's always going to interpret it like that. But if that 2C was not there, so if I made this EA and it was a knock instead, so you'll see that it still has the load A27 in there as well. You see there. So basically what it's doing is this command bit 27A9 is 3 bytes. It's 2C followed by A9 followed by 27. And when the program counter points to this location here, it sees bit 27A9. However, when it points to this location here, it sees load accumulator with 27. So it's just tricking the 6502 into jumping into the middle of a bit instruction. Yeah. The fact that the first thing they did with the kernels. So I read something that it was a spelling mistake in the original documentation, and it just got copied and copied and copied, and so it ended up being called like that. It is just literally just a spelling mistake that's just stuck, which I think is kind of funny. Okay, so that's an interesting way to do that. I'm trying to think of what else I can show you with branches. Anyone else got any branch or compare stuff they want to talk about, or want me to talk about even? I'm trying to think what else is useful with bit. Trying to think of something else. I'm the fat man. I got a Commodore 60 emu. That's the thing. That's awesome. Yeah. What's the least useful branch instruction? Okay, I would probably say the branch of overflow. I would say BVC and BVS. They do get used, but not very often. I got into a habit, and it's quite a bad habit as well, of if I wasn't sure of what say I wanted to jump to here, I got into a bad habit of doing this branch of overflow clear jump location instead of using jump. And what I realized was that works in almost all cases until you start jumping after doing addition. Branching minus is useless because you can't tell if a number is negative or positive. Numbers aren't either. Numbers are just binary it's just a list of binary digits. All branching minus is doing is checking that bit 7. So yeah, branching overflow does become useful with a bit instruction, but to be honest, it's only really useful if you're testing bit 6, in which case, is it really that useful? I mean, if you're testing bit 6, you're probably testing bit 7 as well, in which case you may as well, and you probably tested bit 5 and bit 4, you're probably testing the upper 4 bits, for instance, in which case you may as well just shift them off and test with the carry flag. Stop putting numbers in a box, it's their choice. Yeah, unfortunately numbers are binary. They're not non-binary, they're definitely binary. So yeah, I think that's, for me, that's probably my least used branch. So there is, I think, what other branch instructions are? That is all of them. There are no other branch instructions. Yeah, I mean, the other ones I kind of use. Branch if not equal, branch if equal, definitely the most used. I would say branch if plus is probably my next most used because I like to count loops backwards, and branch if plus is used a lot on that. Then you've probably got branch if carry clear and branch if carry set. It's probably my next one for doing comparisons. Then branch if minus, and then probably the branch if overflow. I'll tell you what I'm gonna demonstrate now. I'm gonna show you something. It's not really to do with branching, but I just want to see if this works because I was reading about this today. I kind of knew about it, but I wasn't really thinking about using it in any particular way. And then it just, I read something today, and I would like to test it out, so I might as well do it on stream. So let me just bring up the vectors. Don't know which one it is though now. Oh god, I have no idea which one it's going to be. All right, never mind. I'll look into that in a bit more detail. Yeah. So what I basically read was you can set a vector so that when you do brk, a vector gets called. Now this takes 1 byte, whereas this takes 3 bytes. And the advantage is if you call this function a lot, you can replace all the calls to this function with a brk by setting that vector, and then you save tons and tons of bytes as you go through, which is kind of interesting. But I need to investigate how that works. I think it might share with the raster interrupt, in which case you would need to do something like this. You would need to push the processor stack on, pull it off, and then you would probably need to check some bits to see if it's a break instruction or otherwise. I'll do some investigation. I need to do a bit of optimization around the Saturday game probably. So I might implement some things like this because there's a lot of this going on in the game, and this definitely saves bytes and cycles. I definitely want to do this as well. I think this would probably save a lot because I'm pretty sure there's a lot of cases where I'm testing bits. I'm testing values, and I'm destroying registers, whereas I don't actually have to destroy any registers. So I've probably got some like store X in temp or some push and pull somewhere. Yeah, okay. Let's. So we discussed briefly about branches taking more than 2 or 3 cycles if they cross a page boundary. So let's explain that a little bit. So sometimes you need your code to align neatly to a location. So imagine we have a table here, and this table contains all the numbers Oops. What can I call this? Let me just give this a bit of a name as well. So, so you might want to address something in this table, you know, like this, and you might do something like that, right? And that's fine. That's a common way of doing this. But you may have another way that you want to address this using using self-modified code, for instance, right? So say for some reason you need to look values up in this table using self-modified code. So what you might want to do is basically address this table just with the lower byte as well. And this is quite common in Z80 as well, I think. So you install this at mod +1, and then this will grab a byte in this table. However, will only work if this table starts at 00, something 00, so XX 00. That's just one kind of crazy case. Another case might be, yeah, God, I'm trying to think. 0316, 0317. Ah, okay, cool. Let me just look those up. Let's just an address of the break service routine. Ah, okay, cool. Yeah, so I can use that. So let's keep the self-mod example in. So if I was to run this now, and store that at 0400, right? So 5 is the letter E. So we would expect the letter E to appear on screen when I do this. However, it's not going to because of the self-mod, the way the self-mod works. Let's do this in, actually, yeah. You see, we've not got an E, we've got this weird arrow symbol. And the reason we've got this weird arrow symbol is because this value here is not aligned. So what we'd actually have to do is we'd have to work out a 16-bit value for this, and that's going to be very inefficient. So instead what you can do is you can align this table. So let's run it in the debugger and show you where it is. Why is that not loaded? Oh, because I've still got it open. Here we go. There we go. It is open already. Let's go and have a look at what it's actually doing. So you can see here, we've told it to change this lower byte to 05, which it has done. And so the address it's come up with is 0805, and that's up here, but the table starts here. You see how the table starts at 081E? So that's not going to work as a self-mod solution. You would have to actually work out the value properly indexed off from there. But if we align this table to the closest, to the next page boundary, so this is a page boundary, because 100 is 256, which is at a page boundary. It will align that code to the next page boundary along. So when I go and have a look at this, we should see 0905 instead. And you can see there 0905. So what it does, it align. You can see it the RTS is here, and then it just a load of junk in here, and it just keeps going until it aligns. And you see here it aligns 0900. It's matched this this pattern basically, and then the table fits in here, and the numbers go, and so that value is now an E on the screen, and it works correctly. You don't always have to align to 100. You can align to any value that you want to. So another example might be you have, and I think I do this in the game. So say I've got some game strings here, and I might just have some values like this. So these strings are all kind of random lengths. So if I wanted to grab the third string in here, I'd have to know where each one started. But what I could also do is I could look at the longest one here. I could say, okay, this is 7, 8, 9, 10, 11. 11 bytes long, right? So instead what I can do is I can align these nice and neat. I don't have to align the first one because that starts here. But if I align all the rest by the exact same amount, and I'll do it by 16, it's a nice round number when it comes to hexadecimal. That means each one of these strings is now exactly 16 bytes long. I can keep putting values in here and it will just align it to the closest one. If I go longer than 16, it will break, but basically it's allowing me to align those strings, and then I can very easily go, okay, load accumulator with 02, which is my string number. I need to times it by 16 to get the offset, so I'm just gonna shift it to the left 4 times and transfer that to the X register. And now when I do game strings, X, I'll get the first value in this string here as well. You see my stream where you can insert a label in the middle of the sum code as new +1. Seriously, you can do that? I did not know you could do that. Oh my god, right, I need to test that. That's something I did not know. Wow, okay, that's really cool. Oh, extra points for old school code for that. That's really good. So I'm going to write I just want to see that. That's kind of cool if that works. Holy shit, that's amazing. Bonus points. That's made me really excited, that. I like that. My only concern is it does make it a little bit less readable. Like, okay. Yeah, I do really like that, but I do worry about its kind of maintainability. So imagine this code is way off down here somewhere. If I look at that, it's not immediately obvious that this is updating a self-modifying address. I mean, yes, I can call this, you know, self-mod or something. But it might, yeah. I like it. I'm not sure if I'm gonna use it or not, but I do like the fact that you can do that. That's kind of cool. Yeah, that's interesting. Yeah, so this is again, this is another use of a line. It's just making sure that each block of data that you've got is the same length as well, so you can do indexing into it nice and easily just by shifting a value like so. We actually use this in the Saturday game for doing the bonus strings that come across the screen, because they're all slightly different lengths. So you can worry less about the big little endian crap now. Yeah. Well, yeah, I mean, this is my problem with it. I like it. I think it's really cool. But I'm probably not going to use it because I think it takes some of the, like, when I read a piece of code, I want to immediately know what it's doing. This is why when I do these kind of additions, I always put a +0. This +0 is completely pointless. It doesn't really do anything. In terms of the assembler, it does nothing. It's the same as doing that. But by writing +0 on there, I know that what I'm actually dealing with is a 16-bit or higher value. And so I know to expect a +1 somewhere else. It's just about kind of about kind of looking ahead and finding those well, not looking ahead, but looking at code and being able to understand as quickly as possible in as few lines as possible as what's going on. But I don't know, man. I don't know. I kind of want to use it now. I feel like it's something I didn't know about and I want to use. Right, I'm going to go for a quick smoke. When I come back, I don't know what to do when I come back. Yeah, I use beef all the time. That's what I use. And interestingly, you can also, so if you're doing self mod, you might do something like this. Again, it's down to being able to look at something. If I see that in my code, I know that is going to be a self modded location. So beef to me is the marker for knowing that it's self mod. But interestingly, what you can do as well is you can also do it in immediate mode as well. So this basically will still work as a self mod immediate mode location, but obviously it's only going to use those two that byte there and not the upper byte. But this will compile perfectly fine, and it will just be a single byte here and a single byte here as well. But it makes it easy for me to look at and go, okay, that's going to be a self mod location as well. I'm not vegan. I'm eating chicken now. Did you talk about zero page much, or is it not for the stream? No, it's probably not for the stream. I am running out of things to do with branches and branches, comparisons, and flags. So if anybody has got, I'm going to go for a quick smoke again. If anybody has got an idea of something I can cover, we'll take a look at that. If not, I might just have a go at doing this break thing, because I think it's probably nice just to see if it works or not. Yeah, all right. I'll be back in a minute, guys. Be right back. Okay, I'm back. He's just putting face feed babe decaf. Oh, I like that one. Or coffee. Yeah. Fat ass. Boobies. Yeah. And the thing is, any of these will work as well for self mods, because you're basically going to change them, so it doesn't really matter what you put in here. So, this is perfectly valid. It's all this will do. We'll just use these bytes when it. Oh, let's go and have a look. So let's see what that actually puts into memory. I suspect it's going to do E5 B1. We've got loads of aligned stuff as well, isn't it? So it's going to be down here a little bit. Entry, here we go. Yeah, B1 E5. So it's just taking that bit there. Testing 16-bit and 32-bit numbers. Yeah, actually, that's not a bad one. It's not something I do very often. So this kind of goes back to what I was saying about a comparison being a subtraction. So depending on what you want to test for. So if you just want to test if one number is higher than the other, then what you can do is you could just do a 16-bit subtraction between the two numbers. So let's do an example of that. So let's get rid of these things. So say we want to know is this number higher or lower than this number? Okay. So what you're probably going to need is you're going to probably need some temporary space to work with here. Oop. I think, anyway, let's have a look. I have to think about this because I don't do this very often, so let's give it a try. Okay, teacher's back. Twitch is pushing me to buy a ticket for 2,000 points. Well, the tickets won't work, I don't think. I hope it's not gonna. Yeah, they're turned off, so you won't be able to use them. In fact, I'll turn them off completely because they shouldn't be in there really. Look. Okay. Yeah, so like I say, I can't remember if I've even done this, to be honest, but let's give it a try anyway. Is SID music on? Yeah, it is on. Turn it up a little bit. How many characters? So it can be as long as you want. It really doesn't matter. I would say it has to be at least 3 for it to work and not turn into a 0-page lookup. Just sat down. I don't know. I've got loads of these open now. What am I doing? I'm just on Sprite tonight. I thought this was Sprite 0 and it's not. That's no wonder I'm feeling all. Yeah, this is not Sprite 0, so I'm on full fat Sprite tonight. It's not good. My own fault, I bought the wrong one. Okay, so I want to test these 2 values. So what I'm going to do is we're going to do the same thing. So remember, comparison is taking the accumulator and subtracting our compare value from it. Now, we're not going to be doing it through the accumulator because we're going to use the accumulator to do this, but we'll do it like so. So we want to do a subtraction. So start by setting the carry flag. And we basically do exactly what we would do with any 16-bit subtraction. So we take our accumulator. This will be A here. So we'll take the lower byte of that and we'll subtract the lower byte of this. And we'll store that in this lower byte here. And then we do the same thing with the upper byte. And actually, I don't even think to do a comparison, we don't need these bits here. I think this should be enough. So let's do a check here. So branch of carry clear. So if it's less than, we'll go to less than. Which will be here, and this will be our more than here. So for more than, we'll set the border to red. Otherwise, we'll set it to green. So is this number less than this? It's not less than this, so we should see a red border if this has worked. This is correct. And if I make this less than, so if I make this like 1, 3, and so, we should hopefully see a green border here, which we do, yeah. So basically, you do the same thing. You do the same comparison that you would do with subtraction. So don't need the temp. The only reason you would need the temp value here is if you wanted to test some other things. So say you wanted to test if the result was negative or not. Which you probably wouldn't do anyway. Testing if the result is negative is not something you would do. But if you wanted to, you could do it here, and then you would. You've got this value in here, and then this value will tell you if it's negative. If this value is negative, then the whole thing is negative. So in this case, this will actually be negative as well. Yeah. So really, extending the comparison to 16 bits or more is just about emulating the same thing that the compare does. I recognise this tune. Oh, it's Light Force, that's right. Full fat sprites, yeah. Sounds Sprite's want to get more drink. Yeah, Sprite doubling makes it. Oh my god, you guys. I think that answers the question with comparing. In fact, you still don't need the temp value here at all. So you don't need that temp value at all. So let's just put a note in up here. Okay, anything else that people want me to take a look at? I think the break thing I'm gonna take a look at some other point and probably discuss it at a later date. Let's put the SID request on. Oh my god, this how has it not got Ocean Loader 1 in here? Oh, there it is. Just give it a tiny bit of volume. Yeah, and I mean extending this to 64-bit is just extending this to 24 or 32 is just a matter of adding more things in here as well. I think, can I do D word? Should still work. Same. So D word just means double word. It's just 2 words basically. So 4 bytes instead of 2. But the same thing applies. You just do the subtraction like this, and then you can do a compare like that. If you wanted to compare, if you wanted to test if a number was net positive or negative, so testing 32-bit signed number. So say you want to know if this number is negative or not. Actually, let's do a quick check. Just gonna check that this works with negative numbers as well. So if this number is negative, this is now less than this, so we should get a red border hopefully when this runs. Now we get green. Oh, because this is unsigned. So to do a signed check, you would also have to check. No, hang on. Would you check the overflow here? What would you check? Put it on 2 times speed, but sounds like it's playing. No, it's in PAL mode. It's definitely in PAL mode. Is there another version of it? No, that's the only version I've got. It doesn't seem to be in 2 times mode. It seems... Oh, let's do the next ocean loader. There you go. we're not testing sign numbers, so it's fine. Any less common tricks you can do with flags? I'd say the most useful flag is definitely the carry flag. You can do some pretty cool stuff with the carry flag. So for instance, if you want to do if you've got 8 bits like so, and you want to roll them, so you want this to end up being this by rolling this to the left. This doesn't work because this goes into the carry flag. So what you actually end up with is this, and the carry flag. The carry set here. So if you want to roll to the left and you want it to be an 8-bit roll, what you would do is you would take a number like 1, 2, 3, 1, like so, and you would roll this to the left like so, and then if the carry is clear, you would jump to here. But if the carry is not clear, then you would add 7F. So the reason you add 7F is because the carry is set at this point, but this would basically turn this byte on according to this. So this is an 8-bit roll left, and an 8-bit roll right is even easier. So an 8-bit roll right is basically you roll it again like this, and then you just add 0. And what this will do is if the carry gets set, then it will add 1. If the carry is not set, then it will add 0, and that will basically roll these two. So that's another trick that you can do with the flags. Right. He is tired. Rock and roll. So, but that's the problem. Yeah. I am sober. Sober is never good when I'm trying to do code. I do prefer to be drunk. I'm high on sugar, apparently. Let's go through the Ocean Loader tunes. Where's Ocean Loader 3? Okay. I'm kind of running out of ideas for tonight now. Trying to think any other interesting things you can do with the flags as well. I suppose it's making you lose stamina. I mean, there's a few interesting things in there. As I say, I will push this into the repo when I'm done. CC there, put that back there again. What's Sandy saying? Interrupts auto push and then RT. Interrupts auto push, then and RTI auto pull them. I don't know what you're saying here. Interrupts auto push. Oh, the flags. Okay, yes. So. Yeah, so we do have these two instructions, and pull. So for instance, if I did set carry flag here and then did this, and then clear the carry flag, at this point the carry is clear, and this pushes processor states flags to stack. And then when you do a PLP, it will pull these back off again. So at this point, the carry gets set again. It's set here just before we pulled it. Now, the reason why these exist is so you can kind of do kind of complex branching and stuff. But it's worth noting, and this is something I only realized recently as well. I guess I kind of knew it, and I just didn't really think about it very much. Is when you jump to an interrupt, then the very first thing that happens is a push processor. stack. That's what happens. There is no, it isn't anywhere. It just happens as part of the interrupt call. And when you do an RTI, the first thing an RTI does is pull the processor status off the stack. Except I'm not sure if it actually pushes it onto. Does it push it onto the stack? I'd have to check that. I'd have to check if it actually pushes the processor status onto the stack. Yeah, exactly. Break does set that flag. So, but yeah, I'm pretty sure these do push them. I'm pretty sure the interrupts do actually push the value into the stack. I don't think it stores it somewhere else. I think it is the stack that it gets pushed onto. So it pushes that onto the stack as well as your return location as well. Which is the stack pointer. Yeah, okay, it does push because the stack pointer means 3 bytes. Yeah, so that's flags and the stack. There you go. Yeah, I can't remember what order they are as well. I would assume it's the processor status flags last. I think it will push your current program counter, then your processor stack. I think, anyway. I'd have to have a look. But I can't bother setting an interrupt up there. Talk about pick and mix. How are we doing with that? Yeah, so we've been doing the sounds pick and mix. It's looking pretty good. I think we've got like a handful of the sounds in. Prince Faye sent me the latest files, so I'll drop them in this weekend. We'll try and add all the sounds in that we can. I think we should be able to get them all in. I don't see any reason why not. And then we'll start looking at some behaviors, because I want to get as many of the enemy behaviors in as I can, so that I can build a level editor, a map editor, so we can actually put the maps together as well. I want to remove. I know I spent probably like a stream and a half doing this, but I'm going to remove it anyway. So we had some code that created the absorb frames for the sprites, but I realized you can't actually tell. It happens so quickly, you can't actually tell what they are anyway. So I'm going to make like a generic kind of absorb animation, and put that in, which will free up a lot more room for doing behaviors in the intro and stuff, because we're running out of room really quickly, and I kind of want to avoid using compression if I can help it. And I think compress the levels, yes, I can see that being useful, but I don't really want to start kind of compressing intro code and putting it somewhere, and I'd rather keep everything kind of uncompressed except for the levels. So yeah, I'll do the sounds this weekend. I will add the remaining sounds in, and then we'll start looking at behaviors. I think trying to get as many of them in, because we need to start getting a feel for how the levels play out. Are they too easy? Are they too difficult? Interrupt push order is push high byte, push low byte, push. Yeah, that's what I suspected, to be honest. Oh god, I remember this. Oh, this is the remix. Hang on, let's go to Ocean Load of Fallen. Okay. I think I might call it a night there then. I don't think I've really got much more to add to this. I'm trying to think if there is anything else I need to cover. I think this is it. I was kind of suspecting this might be a bit short, this stream. I'm just surprised how quickly I went through the description of the branch instructions, to be honest. Trying to think if there's any other little tricks that I can show you that use the flags. Not really, no. Oh, I already showed how to half a sign number. And did I keep that in here? I bet I didn't, did I? No, let's put that in here as well. So, half a signed number. So this is what I showed you before. So if you take a number like C0 and you want to half it, if you just do logical shift right, you're going to get 60 out the other end, which is incorrect. So instead what you do is you set the carry flag. Sets carry if the number is negative, and then you do a raw there, and that will half a sign number properly for you. If I could have one more flag, what would it be? Oh, that's a good one. Not sure. What do I? It would probably be an unsigned overflow. So the overflow flag happens when a number goes from let's go back to the number line here. So it happens when you go when you cross this boundary here, basically, or this boundary. But I'd also like an overflow flag here as well. The reason why I'd like that is I'd like it to work with increase and decrease. So if you decrease a number from 0 to FF, it sets that overflow flag. You can kind of do it with carry flag as well, but that's no good for kind of increments, because increments don't affect the carry flag. So please kind of explain that half negative number. Yes, sure. So if you've got a negative number, right, this is what it looks like. So this number looks like this. So this is the sign bit. This tells us that it's a negative number, and then this is the 2's complement, which makes it up. So this is negative 64. So if we compare it with 80, what we're basically doing, we're saying if it's 100 or more, then it's negative. So this is basically set the carry if the number is negative. So then what happens when we roll it is this number gets rolled like so, but the carry flag also gets put into this location. So what that means is if the number is negative, then it will remain negative. If the number is positive, then it will stay positive, because this will either be 0 or 1 depending on whether the carry flag was set. And so what this does is because of the way 2 complement work, it means that this number here now, it's minus 32. Because the negative flag is set, and then this bit is 32 and 2's complement. So carry flag is only affected by operations on accumulator. Yes, that's correct. Again, you can look at the I've closed it. Let me reopen. You can look at this where is it gone? You can look at this and you can see which things affect it. So add and subtract. Actually, no, comparing X and Y also affect it. So all the compare instructions affect it, which makes sense because it's essentially doing a subtract. Add and subtract do it, but you can see that the decrease doesn't, decrease Y doesn't, increase X, increase Y doesn't. Also increment and decrement don't as well. Interestingly, on the Mega 65, there's an instruction which is just this. So we've got this instruction, and we've got this instruction, but we don't have one for the accumulator. So on the Mega 65, there is that, which normally you have to give in an address, either a 0 page or a full address. But on the Mega 65, it's basically that. So which allows you to do decrement on the accumulator as well, which is kind of nice. But yeah, the carry flag is set by those, obviously by pulling the processor status, return from interrupt, and setting and clearing the carry flag as well. So we've done all the ocean loaders now. All right, I think I'm going to call it a night there, guys. It's been a fairly easy one. I hope I've not gone too fast. I hope the stuff has made sense. The align, is it heavily used by demo? Yes, it will be used. So one of the things you'll see when I did the stable raster code, it's really important to make sure that raster code fits neatly within a page. So that code is all aligned to make sure that it never crosses a page boundary. No matter what you write above and below it, it never crosses a page boundary. Because if you don't do that, you can get into the habit of having that code somewhere imported, and then you write it and it all works, and then you write a piece of code just above it, and all of a sudden it just fails again. So yeah, no problem. Oh, Mitsuyama, I'm still waiting on Sam's Journey, but as soon as it comes, I will get it sent to you. I've figured out how I can send something without leaving the house, so it should be good. Right, let's go and have a look to raid. I need to refresh because I've noticed that the raid doesn't update. Oh, Cola's on. Let's go and raid Cola. I don't know what it's Quake 2 it. So it's got the Quake 2 folder open. If he's actually playing it or not, I hope so, because Quake 2 is an awesome game. Alright, let's go and raid Mr. Cola. Yeah, thanks for coming along tonight, guys, and I shall see you on Saturday. We'll continue with the sound effects and the music on the game, and hopefully get some more behaviours put in. Okay, cool. Right, let's go and raid Mr. Cola now, and I shall see you guys Saturday. Take care.